When we think about the shape of molecules, the theory that we use to help us predict shape is this VSEPR theory. So in your prep chem classes, you should be familiar with the concept of VSEPR. Okay, that's our valence shell electron pair repulsion. Okay, so in prep chem, theoretically, you learned 3 of the 5 basic molecular shapes. Hopefully you learned linear, trigonal planar, and tetrahedral. But as a review, let's just make sure that we remember what this VSEPR theory is before delving into all the different geometries that exist. Okay, so there's a couple ways of looking at VSEPR theory and thinking about the geometry. You can think of it in terms of like the total number of electron groups around a particular central atom, where a double bond and a triple bond and a single bond, all 3 of those count as one electron group. But we can also start breaking it down into understanding the difference between things called sigma bonds and pi bonds. Now, I've introduced the concept of sigma bonds and pi bonds once before, but let's take a look at it in a little bit more, refresher and make sure that we understand what these are. Okay, so the sigma bond, all right, this is the first bond to form between any 2 atoms. Okay, so that's the first bond to form. So a sigma bond always has to form before any pi bonds form. And so the sigma bonds, those are the original linkages that occur between 2 atoms. Okay, so forms between And so what we're looking at is we're looking at this original side-to-side overlap of the orbitals that happens. And so, you've got one atom, you've got another atom, and as they get closer together, their orbitals begin to overlap, okay? And so it's this original side-to-side overlap of these orbitals that forms the sigma bonds, okay? Our pi bonds are the second or third bond to form between 2 atoms. Okay, and pi bonds form above and below the plane of the molecule. Okay, and so when we have a sigma bond or when we have pi bonds, there's a lot of interesting considerations that start to happen when we think about how a particular molecule can behave and how the atoms within an individual molecule can behave. And so we will definitely explore the difference between sigma bonds and pi bonds a lot further as we delve into this topic of molecular geometry and these different theories about how things bond. But just to kind of solidify, so when I think about a molecule, let's take something simple like carbon dioxide. Okay, when we draw Lewis structures, we teach you to, place everything relative around each other at first, and then to draw one bond between each thing, right? Okay, those are the sigma bonds, those initial bonds. Now, as we go through our structure drawing for carbon dioxide, we realize that the only way to get all the electrons to work out is to put in a double bond, and then we've got our lone pairs on the oxygens. Okay, so I'm going to erase my bonds here. Okay, and I'm going to color code here. So I'm going to put these 2 red bonds. And so my red is my sigma. All right, and in blue, okay, and sometimes when we are like writing out a molecule, we might write a sigma or we might write a pi. Now, what if we have a compound that has a triple bond in it? Like what happens if I have 2 nitrogens hooked together? Well, the initial linkage between the 2 nitrogens, that's my sigma bond. And then as I put in my pi bonds there for that triple bond. Both the second and the third bond that give me a triple bond there are going to be my pi bonds. And those are going to happen above and below the plane. So my sigma bonds are this initial end-to-end overlap. And then my pi bonds form above and below the plane. Okay? So let's keep that straight because we're going to come back to this concept between sigma and pi bonds quite a bit as we start to understand some of these different bonding theories and try to understand, how to visualize all these shapes of our molecules. Okay? All right, now to review with VSEPR theory. Again, that's valence shell electron pair repulsion. Okay, our basic principle here is each group of valence electrons around a central atom is located as far away as possible from the others in order to minimize repulsions. Okay, because electrons are all negatively charged, okay? What happens when I put two like-charged things next to each other? Do they attract each other or do they repel each other? They repel each other. All right, and so electrons are all negatively charged. And so they want to minimize the repulsions they feel by being pushed near each other. So they push each other as far away as they possibly can in order to minimize those repulsions. So when we look at the shape of molecules, we have to look at the things surrounding them and put them as far away as possible. And so what we're looking at are the sigma bonds and the lone pairs. Okay, so we're looking at the sigma bonds and the lone pairs. All right, so we have, double and triple bonds and single bonds. And so when I look at these two species here together, we're looking at the number of sigma bonds, not the total number of bonds, okay? And so when I look at something like carbon dioxide or this beryllium dichloride, both of them are linear geometry. So if I look at my carbon dioxide, and I'll use the color coding that I did a little bit ago. Okay, so I have my carbon and my oxygens, and I know I have lone pairs on my oxygens. Okay, I have one sigma bond from carbon out to each oxygen and one pi bond. Okay, when I look at my beryllium dichloride, okay, we've got our lone pairs on here. And so when I look at the central atom on each of these, I have one central atom and two sigma bonds. Okay, and so that's where my linear geometry comes in. It doesn't matter that in carbon dioxide I have double bonds, I still have two sigma bonds off that carbon and no lone pairs. All right, and so we have to look at that when we're assessing our geometries. Now there's 5 basic molecular shapes. Again, in your prep class, theoretically you learned about linear, trigonal planar, and tetrahedral. And now we're going to add in trigonal bipyramidal and octahedral. Okay, so here's our 5 basic molecular shapes with some balloons to help understand the shaping there. And so our linear straight line, so here I've got a linear molecule. Trigonal planar, it's a flat triangle, so trigonal, tri, 3. Planar, flat in one plane. Okay, tetrahedral forms a tetrahedron. Now we get into things that are sticking out in multiple places. We have our trigonal bipyramidal. Okay. and then our octahedral. Okay, so now the thing with octahedral to remember is that there's 6 things bonded to the central atom, but octahedral means 8. It's because when I have those 6 things, I have a square up here and then a square pyramid down here. So I have 4 faces on the top and 4 faces on the bottom. 4 and 4 is 8. That's where we get octahedral from, because it comes from the shape of an octahedron. Okay, so those are all the different molecular shapes that we're going to take into account. Now, when we start looking at these, we can understand that sometimes everything's going to be bonding, but sometimes we're going to have a mix of bonds and lone pairs, because remember, our geometry isn't just looking at sigma bonds, it's looking at sigma bonds and lone pairs. All right, now to make this less arduous to sit and watch, I've broken this up into 2 more videos. What I've done is I've broken up the linear, the trigonal planar, and the tetrahedral geometries into one video. This should be review from your prep class. And then I've got the trigonal bipyramidal and the octahedral geometries in a second video. So that way, if you remember your, first 3 really well, you can watch the, next video with a little bit more kind of an overview mind, like, okay, this is review, but then we can get into the trigonal bipyramidal and octahedral in a separate video. So we will review things in the first video, and then and we might touch on some nuances that you may or may not have looked at in prep chem, and then in the video after that we'll do the other 2. And then I have a third VSEPR video where I put everything together in a summary with some example problems. So I've tried to break it up so that we don't have like an hour-long video of just geometry. All right, so my advice to you, it can be a little bit dense. Watch a video, get up and stretch for 5 minutes, and then come back with a fresh mind. Movement's good for you. Exercise wakes your brain up. Sit down, watch a video, take your notes on it, get up for 5 minutes. Okay, break it up a little bit. That way you're not just going, glaze-eyed by the time I get to some of the weirder things that happen, especially with trigonal bipyramidal. This one's interesting because of the way the shape works. We have axial and equatorial type atoms, and where something is located is actually incredibly important on a trigonal bipyramidal geometry. So make sure you're fresh-minded for that one. All right, so this is our introduction to VSEPR. Coming up, we'll take a look at linear, trigonal planar, and tetrahedral geometries.